Let's talk a little bit more about jumps. RISC-V has two types of unconditional jumps, jump and link and jump and link register. And typically unconditional jumps or unconditional branches are called just jumps. So we have jump and link, which writes a destination register with PC plus 4 and makes PC equal to the current PC plus an immediate offset. And so jump and link register, on the other hand, JALR, also writes a destination register with PC plus 4, but makes the jumps to the address held in RS plus a 12-bit sign extended immediate. And so let's talk about how we use these two unconditional jump instructions. Mostly we use them in terms of pseudo instructions. So we actually don't necessarily use all its capabilities, but we use an instruction that it's not actually a RISC-V instruction, but it's convenient for the programmer to use. The assembler will then convert them into real RISC-V instructions. So here are 4 jump pseudo instructions that are commonly used. So here's jump immediate, which is a pseudo instruction. This is the pseudo instruction. It's converted into the real MIPS instruction. Jump and link, well, the destination register X0 will have a value 0 no matter, even if you write to it, right? So PC plus 4 gets written there, but nothing happens because we've defined it that the 0 register always holds 0, and then the immediate will encode where we want to jump to, as we'll talk about later when we talk about machine instructions. And we have jump and link immediate. This is pseudocode for jump and link RA. So RA gets PC plus 4, and then the immediate will encode where we want to jump to. Talk about that later. Jump register RS is, well, jump and link. This is pseudocode for jump and link register RS. 0, the immediate, so we don't add anything to RS, and don't write PC plus 4 anywhere, right? Writing PC plus 4 to X0 will have no effect. And so this jumps to just the value held in RS. And the last pseudocode we have is the return instruction, or RET, which is JRRA, which we know is pseudocode for this itself. So our label indicates where to jump to, and it's represented in jump as immediate offset. So immediate is the number of bytes past the jump instruction. So this is an offset from the current PC. So this program counter, when we execute the jump and link instruction, is hex 300. And so we're going to encode relative to that instruction address, so hex 300, how much further away is it? And it's a signed immediate, so it could be a positive or negative number, right? We could jump forward, so it's a lower to higher addresses, or we could jump backwards to lower addresses. In this case, we're jumping to a label at hex 51C. That's, well, the difference between hex 300 and hex 51C is hex 21C. And so that's what's going to be encoded in the immediate field of that instruction, is the relative address of the target instruction. So the target instruction is where the label is. As we talked about before, immediates are limited in size. So we have a 20-bit immediate for jump and link and a 12-bit immediate for jump and link register. So this is going to limit how far our program can jump. So if we want to jump further than that, then can be encoded in those immediates, then we can use 2 instructions, add upper immediate PC. So AUIPC is the add upper immediate PC, which is RD equals PC plus, well, this upper immediate, this 20-bit immediate in the upper bits and zeros in the lower bits. And we can use that in conjunction with a jump and link register. So this pseudo instruction call and giving the entire 32-bit address is going to give us, behave like a jump and link immediate, but allows for that 32-bit immediate. So we add upper immediate PC, we add some value to the PC, and then, so this RD is going to be equal to this immediate, upper immediate plus the PC. And then we're going to jump and link register to that value plus a lower immediate, or a 12-bit signed immediate. And then this jump and link register RA puts PC plus 4 in RA. So here are some other RISC-V pseudo instructions. We have jump label, which we talked about, which is like jump and link. Destination register isn't written. Put 0 there and just jumps to the label. Jump register RA, talked about that one. And here's a move pseudo instruction. Again, it's not a real RISC-V instruction, but we can implement it. It's basically move says move the contents of register S3 into register T5. Well, yeah, we can do that. It's clear this is a move. I know what I'm doing. Add immediate, I kind of have to parse that a little bit. So it's easier for programmers to use that pseudo instruction, which can be translated later into a simple RISC-V instruction. Not S7 T2 performs the not of T2, the inverse, the ones complement of T2, and puts it in S7. No op does absolutely nothing, which seems like, why would you ever have that if it does nothing? Well, sometimes it's useful to have precise delays, and that's what no ops are most often used for. We actually have a pseudo instruction for loading a 32-bit immediate. It's called load immediate, or LI. And it's those two instructions, load up immediate and add immediate, that we've talked about. Branch greater than, well, we don't have that instruction because we can do the same, right? If S1, this is going to branch if S1 is greater than T3, going to branch to that label. Well, we can do that with the branch less than instruction. T3, branch if T3 is less than S1. Yeah, that's the same. Right? T3 less than S1 is the same as S1 greater than T3. Branch greater than or equal to 0. Branch if T2 is greater than or equal to 0. Well, branch greater than or equal to, and 0 as that second operand there. And so this is branches if T2 is greater than or equal to 0. And call has allows us to make a procedure call to a faraway instruction. So one where we need to encode all 32 bits of the destination address that we're calling. And return is jump register RA, which is also written like that. That's the real instruction, but also the same as the other pseudo instruction JRRA.